There is something moving through the solar system right now that does not make sense. Not in the way that puzzles are unsolved or mysteries remain open, but in a more fundamental way. The object known as 3I/Atlas, the third confirmed interstellar visitor ever detected, has been under continuous observation since its discovery in late 2024. For months, astronomers tracked it, measured it, cataloged its trajectory, and filed it into the growing catalog of objects that arrive from beyond our star. It behaved, for all intents and purposes, like a large, dark, inert mass coasting through space on a path dictated purely by gravity. Then, in the final days of December 2025, a team of researchers confirmed something that had been suspected but not yet verified. The object was accelerating, not in the dramatic, visible way that comets do when they flare and fragment, but subtly, persistently, in a manner that could only be detected through painstaking analysis of its changing velocity over time. This confirmation arrived quietly, buried in technical data releases and preprint servers. But its implications have begun to ripple outward through the astronomical community with a kind of hushed urgency. Because the acceleration itself is not the problem. Comets accelerate all the time. The problem is what that acceleration reveals about the mass of the object. And what it reveals is impossible. To understand why this matters, you have to step back to the beginning of 2025, when 3I/Atlas was still a curiosity rather than a crisis. The object had been discovered months earlier, identified as interstellar based on its hyperbolic trajectory, a path that would carry it through the solar system and back out into the void without ever returning. Early observations were focused on nailing down that trajectory with precision, ensuring that the object's origin was truly extrasolar and not some deeply eccentric solar system body that had been perturbed into an unusual orbit. Those observations succeeded. The trajectory was confirmed. The interstellar origin was undeniable. But in the process of refining that path, astronomers also began to accumulate data on the object's brightness, its reflectivity, and its behavior over time. Brightness, in astronomy, is one of the primary tools for estimating size. If you know how far away an object is, and how much light it reflects, you can infer, with reasonable confidence, how large it must be. The brightness data for 3I/Atlas, combined with assumptions about its surface reflectivity, suggested an object several kilometers across. Not enormous by solar system standards, but substantial. A body large enough to have significant mass, large enough to hold itself together under its own gravity, large enough to behave, essentially, like a small asteroid or a dead comet nucleus. For months, that picture held. The object moved predictably. Its brightness remained stable. There were no signs of outgassing, no visible coma, no tail, no sudden changes in albedo that would suggest active sublimation of ice. It looked, in every measurable way, like an inert chunk of rock and metal drifting through the inner solar system under the influence of gravity alone. This was not surprising. Interstellar objects are expected to be cold, ancient, and largely inactive by the time they reach us, having spent millions or billions of years in the deep freeze of interstellar space. The first interstellar object, 1I/Oumuamua, also exhibited non-gravitational acceleration, and it too defied easy categorization. It was tumbling rapidly, it had an unusual elongated shape, and it showed no signs of cometary activity despite accelerating in a manner consistent with outgassing. That mystery has not been fully resolved. Multiple competing explanations exist, ranging from a nitrogen iceberg to a hydrogen iceberg to a fractal dust aggregate to more exotic proposals involving solar radiation pressure acting on a thin, reflective surface. None of these explanations have been definitively confirmed or ruled out, and the object is now too far away and too faint to gather more data. The experience with Oumuamua taught the astronomical community several important lessons. First, that interstellar objects can be strange, that they can have properties and behaviors that do not fit neatly into our existing taxonomies. Second, that the window of observation for these objects is brief, that we must act quickly to gather as much data as possible before they fade from view. And third, that conventional wisdom developed from studying solar system objects may not apply directly to visitors from other stars. With Oumuamua, one of the key puzzles was its shape. Observations of its brightness variations as it tumbled suggested an extremely elongated object, perhaps 10 times as long as it was wide, resembling a cosmic cigar or needle. Such extreme elongation is rare among solar system bodies. Most asteroids and comets are irregular but roughly equidimensional, not dramatically elongated. The unusual shape led to much speculation about its origin and nature. Some suggested it was a fragment of a larger body that had been tidally disrupted during a close encounter with a star. Others proposed it was a naturally elongated object formed through some process we do not fully understand. The shape also influenced estimates of its mass and density. An elongated object has more surface area relative to its volume than a spherical object, which affects how solar radiation pressure acts on it, and how much thrust a given amount of outgassing would produce. For 3I/Atlas, the shape is less clear. The variations in brightness over time are relatively modest, suggesting that the object is either not tumbling rapidly or that its shape is not extremely elongated. If it were shaped like Oumuamua, we would expect to see larger variations in brightness as different aspects of the elongated body came into view. The fact that the brightness is relatively stable suggests a more compact, possibly more spherical shape, but this makes the mass discrepancy even harder to explain. A spherical or nearly spherical object has the smallest surface area for a given volume, which means the smallest reflective area for a given mass. If 3I/Atlas were highly elongated, you could argue that its large surface area explains why it appears bright despite having low mass. But if it is roughly spherical, that argument does not work. The brightness would then directly reflect the cross-sectional area, and the cross-sectional area would scale with the square of the radius, while the mass scales with the cube. There is no geometric trick that can reconcile a brightness implying several kilometers diameter with a mass implying 1 kilometer diameter if the shape is compact. Then came the acceleration data. Non-gravitational acceleration is detected not through direct observation of thrust or visible exhaust, but through the slow accumulation of positional data over time. If an object is moving only under the influence of gravity, its path can be predicted with extraordinary precision. Any deviation from that predicted path, no matter how small, indicates that some other force is acting on the object. The process of detecting these deviations is both elegant and painstaking. Astronomers photograph the object against the background stars, measuring its position to within fractions of an arcsecond. They repeat these observations over weeks and months, building up a detailed record of where the object has been. Then they compare this observed path to the predicted path, the trajectory that would result if only the sun's gravity and the gravitational influence of the planets were acting on the object. The predictions are generated using numerical integration, solving the equations of motion that describe how gravity from multiple bodies combines to shape an orbit. These calculations are extraordinarily precise. They can predict the position of an object months or years in advance to within kilometers. When the observed position deviates from the predicted position by more than the measurement uncertainty, and when that deviation grows systematically over time rather than fluctuating randomly, it indicates that a non-gravitational force is acting. For comets, that force is typically the recoil from outgassing, the gentle push that comes from ice sublimating on the sun-facing side and jetting away into space. The physics is straightforward. As a comet approaches the sun, its surface warms. Frozen volatiles, primarily water ice but also carbon dioxide, carbon monoxide, and other compounds, begin to sublimate, transitioning directly from solid to gas without passing through a liquid phase. The gas molecules escape from the surface and fly away into space, carrying momentum with them. By Newton's third law, the comet experiences an equal and opposite momentum change, a tiny push in the direction opposite to the escaping gas. For a comet several kilometers across, this push is small, but for a small light object, it can be significant. The magnitude of the acceleration depends on how much gas is being released, how fast it is moving, and how massive the comet is. This is a well-understood process. It happens all the time. It is, in fact, one of the defining characteristics of active comets. The acceleration is usually small, but measurable, and it leaves behind visible evidence in the form of dust and gas that scatter sunlight and create the characteristic coma and tail. What makes the acceleration of 3I/Atlas unusual is not that it exists, but that it exists in the absence of any corresponding visible activity. There is no coma. There is no tail. There is no detectable brightening that would indicate dust being released into space. When a comet outgasses, the escaping gas drags dust particles along with it. These particles, ranging in size from submicron grains to millimeter-sized pebbles, scatter sunlight and create the diffuse cloud that surrounds the nucleus. The coma can extend for tens of thousands of kilometers, and the tail, pushed by solar radiation pressure and the solar wind, can stretch for millions of kilometers. Even modest outgassing produces a visible coma. Even weak activity leaves a trace. But 3I/Atlas shows none of this. The object remains dark and quiet, yet it is accelerating. The positional data is unambiguous. The deviation from a purely gravitational path is real, persistent, and follows the pattern expected for a thermally driven process. As the object approached perihelion, the closest point to the Sun, the acceleration increased. As it moves away, the acceleration is diminishing. This is the signature of solar heating driving sublimation. But where is the gas? Where is the dust? Where is the evidence that should accompany this process? This is where the problem begins to take shape. When you measure non-gravitational acceleration, you are in effect measuring the ratio of force to mass. If you know the force, you can infer the mass. If you assume the force is coming from outgassing, which is the most reasonable assumption given the context, you can estimate how much gas is being expelled and how much momentum that gas is imparting to the object. The calculations are not simple, but they are standard. They have been done thousands of times for thousands of comets. And when those calculations are applied to 3I/Atlas, they yield a mass estimate that is astonishingly low. The acceleration data implies an object with a mass consistent with a body only about 1 kilometer across, perhaps slightly less, not several kilometers. Not a massive inert chunk of rock, a small object, light enough that even a modest amount of outgassing could produce the observed acceleration. This is a problem, because the brightness data still implies something much larger. And therein lies the paradox. If the brightness-based size estimate is correct, then the object is several kilometers wide and should have a mass many times greater than what the acceleration data suggests. If the acceleration-based mass estimate is correct, then the object is much smaller and much lighter, which means the brightness we observe is coming from something far more reflective than expected, or from a surface area much larger than the solid body itself, or from something else entirely that does not fit into conventional models. These two measurements, brightness and acceleration, are both grounded in well-tested physics. Both are derived from real observational data, and yet they point to two completely different objects. The discrepancy is not a few percent. It is not even a factor of 2 or 3. The mass implied by the acceleration is roughly 1% of the mass implied by the brightness. A 99% gap. An object that by one measure should be heavy enough to shrug off the forces acting on it, and by another measure, is so light that those same forces are visibly altering its path. You might reasonably ask whether this is simply a matter of measurement error, whether the precision of one or both techniques is insufficient to resolve the discrepancy. This is a fair question, and it is one that astronomers themselves immediately considered. Measurement uncertainties exist in all observational astronomy. Brightness measurements depend on assumptions about distance, reflectivity, and surface texture, all of which introduce error bars. Acceleration measurements depend on the precision of positional tracking over time, the accuracy of gravitational models, and the assumption that non-gravitational forces are the only unaccounted variable. But the error bars in this case are not large enough to bridge the gap. The brightness data is robust. The positional tracking is excellent. The models are reliable. This is not a case of two marginally inconsistent numbers that might converge with better data. This is a case of two high-confidence measurements that are fundamentally incompatible. One possible explanation is that the object is not a solid body at all, but something more diffuse. If 3I/Atlas is a loosely bound aggregate of small particles, a rubble pile held together by weak cohesion rather than structural strength, then its effective cross-sectional area for reflecting sunlight could be much larger than its actual mass would suggest. This would make it appear bright without being heavy. Rubble pile structures are common among small solar system bodies, particularly among comets, which are known to be fragile and porous. But rubble piles still follow predictable rules. They still have bulk densities that fall within known ranges. And even if you assume the lowest plausible density, something approaching that of freshly fallen snow, the mass implied by the brightness is still far too high to match the acceleration. You would need a density so low, a structure so tenuous, that the object would barely qualify as a coherent body at all. It would be more like a cloud than a rock, a swarm of particles drifting in loose formation rather than a single object. And if that were the case, you would expect to see evidence of dispersion, of the cloud spreading out over time, of individual particles trailing behind or ahead of the main body. No such evidence has been observed. Another possibility is that the object is outgassing far more efficiently than expected, producing a much larger thrust from a much smaller amount of material. If the outgassing is highly directed, if it is concentrated in narrow jets rather than spread evenly across the surface, then the momentum transfer could be unusually large. This is known to happen with some comets, where localized vents create asymmetric forces that can dominate the object's motion. But directed outgassing typically leaves behind visible signatures. Jets are detectable. They create bright spots or streaks in images. They produce variations in brightness as the object rotates and different jets come into view. They leave behind trails of gas and dust that can be mapped and modeled. None of this has been observed with 3i/Atlas. The object remains dark, featureless, and remarkably consistent in its brightness over time. If it is outgassing, it is doing so in a manner that produces thrust without producing visible ejecta, which is difficult to reconcile with our understanding of how comets work. A third explanation is that the object has undergone catastrophic mass loss, that it was once much larger and has recently shed most of its material, leaving behind a small light core that is now accelerating under forces that would have been negligible when the object was intact. This scenario would explain why the brightness initially suggested a large body, because the observations were capturing light from a cloud of debris surrounding a much smaller nucleus. It would also explain the acceleration, because the remaining core would be light enough to be pushed around by even modest outgassing or radiation pressure. But if this were the case, the debris cloud itself should be visible. Fragmentation events are dramatic. They produce expanding shells of dust and gas that remain detectable for weeks or months. They cause sudden changes in brightness, either brightening as fresh material is exposed, or fading as the debris disperses. They leave behind multiple fragments, trailing along the same orbital path. Observers have been watching 3i/Atlas continuously. No fragmentation event has been recorded. No debris cloud has been detected. No secondary fragments have appeared. The object's brightness has remained stable. If it lost 99% of its mass, that loss was somehow silent, invisible, and complete. Each of these explanations solves part of the problem while creating new contradictions. A diffuse rubble pile would explain low density but not the lack of dispersion. Efficient directed outgassing would explain the acceleration but not the lack of visible jets. Catastrophic mass loss would explain the brightness acceleration mismatch but not the absence of debris. And this is where the situation becomes genuinely unsettling, because it is not that we lack hypotheses. It is that every hypothesis we have requires the object to be behaving in ways that leave detectable traces, and those traces are not there. The object is accelerating as if it is small, appearing bright as if it is large, and showing no evidence of the processes that would reconcile those two facts. It is worth pausing here to emphasize what acceleration data actually tells us. When we measure non-gravitational acceleration, we are not guessing. We are not relying on indirect proxies or rough estimates. We are tracking the object's position with high precision over an extended period, comparing those positions to the predictions of gravitational models that account for the Sun, the planets, and every other known body in the solar system. The deviations from those predictions are real. They are measurable. They are consistent across multiple observation sessions from different telescopes in different locations. The mathematics here is not speculative. It is the same mathematics that allows us to navigate spacecraft to distant planets, to predict eclipses centuries in advance, to map the orbits of thousands of asteroids with extraordinary accuracy. When that mathematics tells us that an object is deviating from a purely gravitational path, we can trust that deviation is real. And when we use that deviation to infer the mass of the object, the uncertainties are well understood. The mass estimate derived from acceleration is not perfect, but it is not wildly uncertain either. It places the object in a specific range, and that range is incompatible with the mass implied by the brightness. Similarly, brightness measurements are not arbitrary. They depend on well-calibrated instruments, on careful photometry, on corrections for atmospheric effects and instrumental biases. The brightness of 3i/Atlas has been measured by multiple independent observers using different telescopes and different techniques. Those measurements agree. The object is consistently reflecting a certain amount of sunlight, and that amount of reflected light, combined with reasonable assumptions about surface properties, yields a size estimate. The process of photometry is more subtle than it might first appear. When a telescope captures an image of a distant object, that image contains information not just about the object itself, but about everything the light passed through on its way to the detector. The Earth's atmosphere scatters and absorbs light. the telescope's optics introduce their own distortions. The detector, whether a CCD camera or some other imaging device, has its own response characteristics, its own quirks and biases. All of these effects must be carefully accounted for before the raw brightness measurement can be converted into a meaningful physical quantity. Astronomers calibrate their measurements by observing standard stars, objects whose brightness is precisely known, and comparing the measured brightness to the expected value. This allows them to determine the atmospheric extinction, the dimming caused by the atmosphere, and to correct for it. They also observe the object multiple times on different nights under different conditions to verify that the measurements are consistent and reproducible. For 3I/Atlas, this process has been carried out by multiple teams using multiple telescopes in multiple locations. The data is robust. The uncertainties are well understood, and the conclusion is consistent across all observations. The object reflects a certain amount of light, given its distance from the Sun and from Earth, both of which are known with high precision. That reflected light implies a certain physical size. The assumptions are not without uncertainty. The reflectivity of the surface, known as albedo, can vary significantly depending on composition and texture. A dark, carbon-rich surface might have an albedo of only a few %, absorbing most of the sunlight that hits it. A bright, icy surface might have an albedo of 50% or more, reflecting half the incident light. The albedo affects the size estimate inversely. If the albedo is lower than assumed, the object must be larger to reflect the observed amount of light. If the albedo is higher than assumed, the object can be smaller. For typical comets and asteroids, albedos range from about 3% to about 40%, with most objects falling somewhere in the middle of that range. When astronomers estimate the size of an object from its brightness, they typically assume an albedo based on what is known about similar objects. For dark inactive bodies like asteroids, they might assume an albedo of 10%. For icy bodies like comets, they might assume 20 or 30%. But even accounting for this range, even pushing the albedo to the extremes of what is physically plausible, the size estimate does not shrink enough to match the mass estimate from the acceleration. You would need an albedo far higher than any natural surface we have ever observed, higher than fresh snow, higher than clean ice, approaching the reflectivity of polished metal. And if the surface were that reflective, we would see spectral signatures, characteristic reflections at specific wavelengths that would reveal the composition. Light interacts with matter in distinctive ways. Different materials absorb and reflect different wavelengths. Ice has strong absorption features in the infrared. Silicate minerals have features in the mid-infrared. Organic compounds have features in the near-infrared and visible. By observing an object at multiple wavelengths and analyzing the spectrum, the pattern of brightness as a function of wavelength, astronomers can infer what the surface is made of. For 3I/Atlas, spectral observations have been attempted, but the object is faint and the data is limited. No strong, distinctive features have been identified. The spectrum, to the extent that it has been measured, appears relatively featureless, consistent with a dark, possibly organic-rich surface. This is not what you would expect from a highly reflective object. It is not consistent with a surface bright enough to explain the brightness-mass discrepancy. There is another layer to this problem that deepens the mystery. The acceleration of 3I/Atlas is not erratic. It is not random. It follows a predictable pattern, consistent with a force that is primarily radial, pushing away from the Sun as the object approaches perihelion, and diminishing as the object recedes. This is exactly what you would expect from outgassing driven by solar heating. As the object gets closer to the Sun, the surface temperature rises, volatile materials sublimate more rapidly, and the outgassing intensifies. As the object moves away, the surface cools, the sublimation slows, and the acceleration diminishes. This thermal response is the hallmark of cometary activity. It is how we know that outgassing, not some exotic force, is responsible for the non-gravitational motion. But the magnitude of the acceleration, combined with the lack of visible activity, implies something unusual about the outgassing itself. Either the object is releasing gas in a way that produces far more thrust than expected for the amount of material being lost, or the object is losing material so efficiently that it converts almost all of its mass loss into velocity change without leaving behind detectable debris. There is, however, another force that acts on small objects in the solar system, one that does not require outgassing at all. Solar radiation pressure, the physical push exerted by sunlight itself, can accelerate very small particles and, under certain conditions, larger objects as well. Photons carry momentum. When they strike a surface and are absorbed or reflected, they transfer that momentum to the object. For most asteroids and comets, radiation pressure is negligible compared to gravity and any forces from outgassing. But for very small particles, micrometer-sized dust grains or smaller, radiation pressure can dominate, sweeping them out of the solar system entirely. For larger objects, radiation pressure is typically too weak to produce measurable effects unless the object has an extremely low density or an extremely high surface area to mass ratio. Could radiation pressure explain the acceleration of 3I/Atlas? In principle, yes. If the object is extraordinarily light or has an unusual shape that maximizes surface area. This was one of the proposed explanations for Oumuamua's acceleration. The idea that the object might be a thin, disc-like structure, almost like a sail, with a huge surface area relative to its mass. Such a structure would experience significant acceleration from radiation pressure without requiring any outgassing. But for this to work for 3I/Atlas, the object would need to have a structure even more extreme than what was proposed for Oumuamua. It would need to be gossamer thin, a sheet or a foam with almost no mass but enormous reflective area. Natural processes do not easily produce such structures. Ice and rock do not form thin shells or delicate lattices on their own, at least not on the scale of kilometers. And if such a structure existed, it would likely be fragile, susceptible to breaking apart under thermal stresses or tidal forces as it passes through the inner solar system. Moreover, the timing of the acceleration does not quite fit the radiation pressure hypothesis. Radiation pressure is strongest near the Sun, but it does not vary with distance in exactly the same way that thermal outgassing does. Outgassing depends on surface temperature, which is determined by the balance between absorbed sunlight and radiated heat. This balance changes rapidly as the object approaches and recedes from the Sun, creating a sharp peak in activity near perihelion. Radiation pressure, by contrast, depends simply on the intensity of sunlight, which falls off as the inverse square of the distance. The pattern of acceleration observed for 3I/Atlas matches the thermal outgassing profile more closely than the radiation pressure profile, which suggests that outgassing, or something that behaves like outgassing, is the dominant force. But this brings us back to the original problem. If it is outgassing, where is the visible evidence? To illustrate this with a rough analogy, imagine you are watching a sailboat on a lake, and you see it moving steadily across the water. You can estimate the size of the boat by how much light it reflects, how large it appears from a distance. You can also estimate the force acting on the boat by measuring how quickly it accelerates. If the boat appears large but accelerates rapidly, you infer that the wind must be very strong, or that the sail is very efficient, or that the boat is much lighter than it looks. Now imagine that you watch the boat for hours, and you never see any wind ruffling the water, no waves, no ripples, no indication that there is any wind at all, and yet the boat continues to accelerate. You would be forced to conclude that either your understanding of the boat's size is wrong, or your understanding of how it is moving is wrong, or there is some third factor you have not accounted for. This is the situation astronomers find themselves in with 3I/Atlas. The object is moving in a way that requires force, but the source of that force is not producing the expected secondary effects. One hypothesis that has been discussed, though not widely embraced, is that the outgassing is occurring through narrow vents or fissures that are somehow oriented in such a way that the expelled gas does not scatter sunlight efficiently. If the gas is transparent, if it consists of molecules that do not reflect visible light, then the outgassing could be invisible even as it produces thrust. This is not entirely implausible. Water vapor, for example, is transparent in visible wavelengths, and only becomes detectable when it condenses into ice crystals or when it fluoresces under ultraviolet light. Carbon monoxide and carbon dioxide are also relatively poor at scattering visible light. But even if the gas itself is invisible, the dust entrained in that gas should not be. Comets do not emit pure gas. They emit a mixture of gas and dust, and the dust particles, even very small ones, are highly effective at scattering sunlight. The dust creates the coma, the diffuse cloud that surrounds the nucleus, and it is the coma that we primarily observe when we look at comets. For 3I/Atlas to be outgassing without a visible coma, it would need to be emitting gas that is almost entirely dust-free, or emitting dust particles so small that they do not scatter light efficiently in visible wavelengths. This possibility deserves closer examination. The size of dust particles affects how they interact with light. Particles much smaller than the wavelength of light, submicron or nanometer scale grains, scatter light differently than larger particles. They tend to scatter preferentially at shorter wavelengths, in the blue and ultraviolet, rather than across the entire visible spectrum. If 3I/Atlas is producing extremely small dust particles, they might be less visible in optical observations than the larger particles typical of solar system comets. But even tiny particles accumulate. Even if each individual grain is barely visible, a large enough number of them would create a detectable haze around the nucleus. And the process that creates such small particles, whether it is erosion, fragmentation, or sublimation of icy grains, typically produces a range of sizes, not exclusively tiny ones. The ratio of dust to gas, often called the dust-to-gas ratio, varies among comets, but generally falls within a certain range. For typical comets, roughly equal masses of dust and gas are released during active periods, though this can vary by a factor of a few in either direction. Some comets are dust-rich, producing bright, extensive tails and faint gas emissions. Others are gas-rich, with weaker dust signatures. But a comet that produces thrust-through outgassing without producing any detectable dust would have a dust-to-gas ratio approaching 0, which is far outside the observed range for any known solar system comet. Such a comet would need to have a composition or structure fundamentally different from what we have encountered before. Perhaps the ices are located beneath a thick, dust-free mantle of rock or refractory organics. Perhaps the outgassing is so gentle that dust particles cannot be lifted from the surface and only gas escapes. Perhaps the dust that is produced is immediately swept away by radiation pressure and disperses so quickly that it never accumulates into a visible coma. Each of these scenarios is possible in principle, but each is also unusual, and together they would make 3I/Atlas an extraordinary outlier among comets. Another angle to consider is the possibility that the brightness estimate is somehow artificially inflated by geometric effects. If the object has an extremely elongated shape, like a needle or a flat disk, then its cross-sectional area as seen from Earth could be much larger than its actual volume would suggest. A thin disc-oriented façon to the observer would reflect a large amount of light despite having relatively little mass. But objects in space tumble. They rotate on multiple axes. Over the course of weeks and months of observation, we would expect to see variations in brightness as different faces of the object come into view. A highly elongated or flattened object would show periodic changes in brightness corresponding to its rotation. 3I/Atlas has been observed extensively, and while there are variations in brightness, they are relatively small and do not suggest the extreme aspect ratios that would be needed to reconcile the mass discrepancy. Moreover, an elongated shape would not explain the acceleration pattern, which is consistent with a force distributed across the surface rather than concentrated at one end. The question of composition also looms large. If the object is made of something unusually light, some material with a density far below that of typical rock or ice, then the mass could be lower than expected without the size being dramatically wrong. But there are limits to how low density can go. Rock has a density around 3 grams per cubic centimeter. Ice has a density around 1 gram per cubic centimeter. Porous, loosely packed material might have a bulk density of half a gram per cubic centimeter, or even less. But even at the lowest plausible density, the mass is still too high to match the acceleration data. You would need a material with a density approaching that of aerogel, a synthetic substance so tenuous that it is sometimes called frozen smoke. Natural materials do not form with such low densities under the conditions present in space. And if the object were that fragile, that tenuous, it would not survive the stresses of its journey through the solar system. It would not maintain its structural integrity. It would disperse, disintegrate, or fragment under the thermal and gravitational forces it experiences as it approaches the Sun. There is also the timing to consider. The acceleration was confirmed in late December 2025, but the object has been under observation for nearly a year. The acceleration itself is not a new phenomenon. It has likely been present throughout the observation period, but it takes time to accumulate enough positional data to detect and confirm a small, persistent deviation from a purely gravitational orbit. The process of confirming non-gravitational acceleration is inherently slow and requires patience. Each position measurement has an uncertainty associated with it, arising from atmospheric seeing, tracking errors, and the finite resolution of the telescope. Any single measurement might show a small deviation from the predicted position, but that deviation could easily be just noise, just the accumulated effect of small errors. Only by collecting many measurements over an extended period can astronomers distinguish between random scatter and a genuine systematic trend. Statistical tests are applied to determine whether the deviations are consistent with a model that includes a non-gravitational force, and whether that model provides a significantly better fit to the data than a purely gravitational model. The threshold for confirmation is high, typically requiring that the non-gravitational acceleration be detected with a confidence level of 5 sigma or better, meaning that there is less than 1 chance in a million that the signal is due to random noise alone. The confirmation came not because something changed about the object, but because the data finally reached the threshold of statistical significance needed to rule out observational noise. This means that the object has been behaving in this contradictory manner for months, perhaps for its entire transit through the inner solar system. It has been simultaneously appearing large and acting small for the entire duration of our observations. And if the object has been shedding mass during this time, either through outgassing or fragmentation, we should see a trend in the brightness, a gradual fading as material is lost and the reflective surface area decreases. No such trend has been reported. The brightness remains stable. At this point, it is tempting to invoke some exotic explanation, to suggest that the object is made of something we have never encountered before, or that it is behaving according to physics we do not yet understand. But science does not work by jumping to the unfamiliar when the familiar becomes difficult. It works by exhausting conventional explanations, by testing and retesting the data, by looking for overlooked factors or hidden assumptions. And the conventional explanations have not yet been exhausted. They have simply failed to produce a satisfying answer. Each model, each scenario, each adjustment to the parameters brings with it new problems that are as difficult as the original. This is not unusual in science. Many discoveries begin as irritating inconsistencies, as measurements that refuse to agree, as objects that refuse to fit neatly into established categories. Sometimes those inconsistencies resolve with better data. Sometimes they reveal subtle errors in the models. And sometimes they point to something genuinely new. What makes the situation with 3.1/Atlas particularly striking is not just the magnitude of the discrepancy, but the quality of the data. This is not a case of a single ambiguous observation or a marginal detection at the edge of instrumental sensitivity. This is an object that has been tracked continuously by multiple observatories using state-of-the-art equipment. The astrometry, the positional measurements are precise. The photometry, the brightness measurements are well calibrated. The models used to interpret the data are the same models that have successfully described thousands of other objects. The data is good. The methods are sound. And yet the results do not agree. This is the kind of situation that, in the history of science, has sometimes preceded important revisions to our understanding. It is also the kind of situation that can simply reflect the complexity of natural systems, the way that real objects in the real universe can behave in ways that defy our initial expectations without requiring new physics. The scientific community's response has been measured but intense. Papers are being written. Data is being reanalyzed. Alternative interpretations are being debated. But there is also a quiet acknowledgement that this may not resolve quickly, that the answer may require observations that are not yet available, or insights that have not yet been articulated. The object is still observable. It is still moving through the solar system, still accelerating, still reflecting sunlight. More data will be gathered. More measurements will be made. And with each new data point, the picture will either clarify or deepen further into paradox. What is clear already is that 3.1/Atlas does not fit comfortably into any existing category. It is not a typical asteroid, because asteroids do not accelerate in this manner. It is not a typical comet, because comets produce visible activity when they outgas. It is not a rubble pile in the conventional sense, because rubble piles still have mass. It is something else, something that has characteristics of multiple types but does not fully conform to any of them. And this brings us back to the central question. What is 3.1/Atlas? If it is as large as it appears, then it should not be accelerating as much as it is. If it is as small as it behaves, then it should not be as bright as it is. One of these two measurements must be wrong, or both must be capturing something real but incomplete. Perhaps the brightness is being enhanced by something we are not seeing, some structure or feature that increases the reflective area without adding proportional mass. Perhaps the acceleration is being driven by a mechanism that is more efficient than standard outgassing, that converts a small amount of mass loss into a large amount of momentum. Perhaps the object is in the process of transforming transitioning from one state to another, and we are observing it during that transition, seeing a snapshot of a process that is not yet complete. But none of these explanations, as stated, have enough detail to constitute a testable hypothesis. They are placeholders, frameworks for thinking about the problem rather than solutions to it. There is a particular kind of discomfort that arises in science when the data refuses to conform to expectation. It is not panic in the colloquial sense, not a sense of immediate danger or existential threat. It is a quieter, more persistent unease, the realization that something fundamental might be misunderstood. Astronomers are not panicking because they think 3I/Atlas poses a risk to Earth. Its trajectory is well understood, and it poses no collision hazard. They are unsettled because the object is challenging the tools and methods that have proven reliable for decades. Brightness-based size estimates work. Non-gravitational acceleration measurements work. These are not speculative techniques. They are foundational to how we study small bodies in the solar system. When those techniques produce contradictory results for the same object, it suggests that something about that object is outside the range of conditions for which those techniques were developed. And if one interstellar visitor can be this anomalous, what does that say about the others we will inevitably discover in the coming years? The first interstellar object, 1I/Oumuamua, also exhibited non-gravitational acceleration, and it too defied easy categorization. It was tumbling rapidly, it had an unusual elongated shape, and it showed no signs of cometary activity despite accelerating in a manner consistent with outgassing. That mystery has not been fully resolved. Multiple competing explanations exist, ranging from a nitrogen iceberg to a hydrogen iceberg to a fractal dust aggregate to more exotic proposals involving solar radiation pressure acting on a thin, reflective surface. None of these explanations have been definitively confirmed or ruled out, and the object is now too far away and too faint to gather more data. 3I/Atlas is still close enough to observe. It is still bright enough to track. The opportunity to solve this mystery, or at least to narrow down the possibilities, still exists. But that opportunity is finite. The object is moving away from the Sun, receding into the outer solar system, and within months it will become too faint for detailed observation. The window for gathering critical data is closing. There is also the question of what this means for our understanding of interstellar space and the objects that populate it. We have now detected 3 confirmed interstellar visitors, and 2 of them have exhibited behavior that is, at minimum, puzzling. This could be a coincidence, a sampling bias resulting from the fact that we are only able to detect the unusual objects, the ones that pass close enough and bright enough to be noticed. The ordinary interstellar objects, the ones that behave predictably, might pass through undetected, lost in the vast catalog of faint, distant specks that fill the sky. Or it could be that interstellar objects are, as a population, genuinely different from their solar system counterparts. They have been subjected to different environments, different histories, different evolutionary pathways. They have spent eons in the cold, dark, radiation-bathed void between stars, exposed to cosmic rays and interstellar dust, and the occasional close encounter with passing molecular clouds. These conditions might alter their composition, their structure, their physical properties in ways that are not immediately obvious when we observe them with telescopes designed to study solar system objects. The interstellar medium is not empty space. It is a dilute but chemically active environment, filled with hydrogen and helium gas, dust grains, complex organic molecules, and high-energy particles. An object traveling through this medium for millions of years accumulates a surface layer of material, a patina of interstellar dust and ice that could alter its reflectivity, its composition, its thermal properties. Cosmic rays, high-energy protons and heavier nuclei accelerated to near the speed of light by supernova shocks and other violent processes, bombard the surface constantly, breaking chemical bonds, creating radiation-damaged layers, altering the crystal structure of ices and minerals. This process, known as space weathering, is well studied for solar system objects, where it darkens surfaces and changes spectral properties over millions of years. But interstellar space weathering operates over much longer timescales and under different conditions. The cosmic ray flux in interstellar space is higher than in the solar system because there is no heliosphere to provide shielding. The temperatures are lower, allowing certain chemical reactions to proceed that would not occur in warmer environments. The radiation environment is harsher, more penetrating, capable of altering material to greater depths. An object that has spent a billion years drifting through interstellar space might have surface layer centimeters, or even meters thick that has been completely transformed by radiation. This layer could be darker, more porous, more enriched in certain elements, or depleted in others compared to the pristine interior. It could have unusual thermal properties, insulating the interior or conducting heat in unexpected ways. It could contain volatile ices that have been created by radiation processing, species like hydrogen peroxide or ammonia that form when cosmic rays break apart water and nitrogen molecules, and the fragments recombine in new configurations. When such an object enters the solar system and begins to warm, these radiation-processed ices might sublimate at different temperatures, different rates, than the pristine water ice we are familiar with from solar system comets. They might produce gas jets that are more or less efficient at generating thrust. They might release gases that are more or less visible. The entire outgassing behavior could be different, subtly or dramatically, from what we expect based on solar system experience. If interstellar visitors are systematically different, then the models we use to interpret our observations may need to be adjusted, expanded, or in some cases, rebuilt from the ground up. The albedo models we use assume surface properties derived from solar system objects. The outgassing models assume compositions and structures typical of solar system comets. The density estimates assume materials and porosities within the range observed locally. All of these assumptions are reasonable starting points, but they may not capture the full range of possibilities. An interstellar object might have a density lower than any solar system body because it spent billions of years in a cold, low-gravity environment where it could accumulate into a highly porous structure without ever being compressed by gravity or collisions. It might have an albedo unlike anything we have measured, because its surface was processed by a different radiation environment. It might outgas in ways we have not observed because its volatile inventory reflects a different formation history, a different parent star, a different planetary system architecture. Each of these factors could contribute to making interstellar objects appear anomalous when viewed through the lens of solar system experience. But it is also possible that 3I/Atlas is not representative of anything broader, that it is simply an outlier, a statistical anomaly that happens to have properties that fall at the extreme end of the distribution. The universe is large. The number of objects within it is unimaginably vast. Among all those objects, some will inevitably have unusual combinations of properties, unusual histories, unusual structures. Not everything needs to fit neatly into a category. Not every object needs to be explained by a single elegant theory. Sometimes things are just strange. But even if 3I/Atlas is an outlier, it is an outlier that we are observing, an outlier that we are trying to understand. And the effort to understand it is pushing the boundaries of our knowledge in valuable ways. Whether or not we arrive at a definitive answer, the process of wrestling with the data, of testing hypotheses, of confronting the limits of our models, is itself a form of progress. The other thing worth considering is the role of observation bias in shaping our perception of this mystery. We are observing 3I/Atlas from Earth, from a single vantage point, using instruments that are optimized for certain types of measurements. We see the object in reflected sunlight, which means we are only observing the side that is facing us and facing the sun. We do not have a view of the entire object. We do not have three-dimensional information about its shape or structure. We are inferring those properties from limited data, from the way the brightness changes over time, from the way the object moves. It is entirely possible that there are features or characteristics of the object that are simply not visible from our perspective, that would explain the discrepancies if only we could see them. A large crater on the far side, a massive plume of outgassing emanating from a region we cannot observe, a cloud of dust or debris that is aligned in such a way that it does not intersect our line of sight. These are not contrived scenarios. They are real possibilities that arise from the inherent limitations of observing distant objects with limited coverage. And yet, even accounting for these limitations, the central paradox remains. The object is either lighter than it should be or brighter than it should be, and the margin of error is too large to dismiss as an artifact of perspective. Another dimension of the problem involves the timescale of observation. We have been watching 3I/Atlas for months, but the object itself has been traveling through space for far longer. Its journey from its home star to our solar system likely took millions of years, possibly billions. During that time, it was exposed to the interstellar medium, to radiation, to micrometeorite impacts, to the slow, steady erosion that comes from simply existing in space for immense spans of time. We do not know what the object looked like when it began its journey. We do not know what processes it has undergone, what changes it has experienced, what material it has gained or lost along the way. We are observing a snapshot, a single moment in a much longer story, and we are trying to infer the entire story from that snapshot. This is always the challenge in astronomy. We cannot rewind time. We cannot follow objects backward to their origins. We can only observe them as they are now and extrapolate, with varying degrees of confidence, what they must have been in the past. The lack of visible debris or fragmentation is particularly striking when you consider how common fragmentation is among comets. Comets are fragile. They break apart regularly, especially when they approach the sun and experience thermal stress. We have observed numerous comets disintegrate in real time, splitting into multiple pieces, shedding large chunks of material, sometimes disappearing entirely. The fact that 3I/Atlas shows no signs of fragmentation despite being subject to the same thermal environment is, in itself, noteworthy. It suggests that the object is either more structurally robust than typical comets, or that it has already undergone fragmentation in the past, and what we are observing now is the remnant, a core that has survived whatever process stripped away the outer layers. But if that process occurred recently enough to explain the mass discrepancy, we should see evidence of it. Debris clouds do not dissipate instantly. They remain detectable for weeks or months, spreading out along the orbit, creating a diffuse trail of material. No such trail has been observed. If fragmentation occurred, it either happened long ago, far from the sun, under conditions where the debris dispersed quickly and completely, or it happened in some manner that left no trace. Neither scenario is particularly satisfying. At some point, we have to confront the possibility that our models, not the object, are the source of the problem. Every measurement we make, every estimate we derive, is based on assumptions. We assume that the object's surface reflects light in a certain way, that its composition falls within certain bounds, that its structure obeys certain physical laws. These assumptions are not arbitrary. They are derived from decades of observation and study of solar system objects. But they are still assumptions, and assumptions can be wrong, especially when applied to objects that come from outside the solar system, from environments we have never directly sampled, from star systems with different compositions and different formation histories. If the assumptions underlying our brightness estimates are wrong, then the size estimate is wrong. If the assumptions underlying our acceleration models are wrong, then the mass estimate is wrong. But identifying which assumptions are wrong, and how to correct them, requires more information than we currently have. It requires knowing something about the object's composition, its structure, its thermal properties, its history, and we do not have that information. We have only the light it reflects and the path it follows. One intriguing possibility that has been discussed, though it remains speculative, is that the object might be composed of materials with unusual optical properties. Certain minerals, certain ices, certain organic compounds can have reflectivities and scattering behaviors that deviate significantly from the averages we use in our models. If 3I/Atlas has a surface that is unusually bright, or a structure that scatters light in unexpected ways, then the brightness-based size estimate could be systematically wrong. We would be overestimating the size because we are underestimating the albedo. But albedo is not a free parameter. It is constrained by the composition. And while there is some variation among natural materials, that variation is not infinite. An albedo high enough to resolve the mass discrepancy would require a surface composition unlike anything we have observed in solar system comets or asteroids. It would need to be almost mirror-like, reflecting the majority of incident sunlight. And if the surface were that reflective, we would expect to see strong spectral features, distinctive absorption or emission lines that would tell us what the surface is made of. So far, no such features have been identified. Though the spectral data on 3I/Atlas is limited, there is also the question of what happens next. The object will continue its outward journey, moving away from the sun and into the cold outer reaches of the solar system. As it recedes, it will fade, becoming progressively more difficult to observe. Eventually, within the next year or two, it will drop below the detection threshold of even the most powerful telescopes, and we will lose the ability to track it. At that point, the opportunity to gather more data will be gone. Whatever mysteries remain unsolved when that happens will remain unsolved, at least until the next interstellar visitor arrives and gives us another chance to test our understanding. The pressure to extract as much information as possible from the remaining observations is high. Every telescope hour matters. Every photon counts. Astronomers are balancing the need to continue monitoring 3.1/Atlas against the need to study other objects, other phenomena, other parts of the sky. The resources are finite, the time is limited, and the questions are urgent. The broader implications of this mystery extend beyond 3.1/Atlas itself. Interstellar objects are relatively new to astronomy. The first confirmed detection was only in 2017 with Oumuamua. Before that, we knew interstellar objects had to exist. The mathematics of stellar dynamics made it clear that objects should be ejected from planetary systems regularly, sent out into interstellar space by gravitational interactions with giant planets. But we had never actually seen one. The detection of Oumuamua changed that. It proved that interstellar objects pass through our solar system, that they are detectable with modern telescopes, and that they can be studied, at least briefly. Since then, the field has exploded. New surveys, new telescopes, new detection algorithms have been developed specifically to find these visitors. The Vera Rubin Observatory, once it becomes fully operational, is expected to detect dozens or even hundreds of interstellar objects over the next decade. We are on the cusp of transforming interstellar objects from rare curiosities into a proper field of study. But that transformation depends on our ability to interpret the data we gather. If we cannot make sense of the objects we have already detected, if our models fail to describe even the handful of visitors we have observed so far, then the flood of new data from future surveys will only deepen the confusion rather than resolve it. And yet, confusion is not necessarily a failure. It is often the precursor to discovery. The history of astronomy is filled with examples of anomalous observations that initially baffled researchers but eventually led to new insights, new theories, new understandings of the cosmos. The anomalous motion of Mercury's orbit eventually led to general relativity. The unexpected rotation curves of galaxies led to the hypothesis of dark matter. The dimming patterns of certain stars led to the discovery of exoplanets. Not every anomaly leads to a revolution. Some are simply errors, artifacts, misunderstandings that get corrected with better data. But some are real, and they change everything. The challenge is distinguishing between the two, and that distinction can only be made through careful, rigorous, patient work, through repeated observation, through testing alternative hypotheses, through building better models and gathering better data. The process is slow. It is painstaking. It does not always yield clear answers. But it is the only process we have. For now, 3.1/Atlas remains an enigma. It is an object that appears large but behaves as if it is small. It is accelerating without visible outgassing. It is reflecting light in a manner that suggests substantial size but experiencing forces that suggest minimal mass. The data is contradictory. The models are incomplete. The explanations are unsatisfying. And that is where we stand, at the beginning of 2026, watching an object from another star as it moves through our solar system, challenging our assumptions and defying our expectations. Scientists are not panicking in the sense of abandoning rationality or descending into chaos. They are panicking in the quieter, more profound sense of realizing that something they thought they understood is not as simple as it seemed, that the universe once again is demonstrating its capacity to surprise us, to present us with puzzles that do not yield easily, that require us to question our tools, our methods, our fundamental assumptions about how things work. The feeling is reminiscent of other moments in the history of astronomy, when observations refused to conform to theory. When Galileo first pointed his telescope at Jupiter and saw moons orbiting another planet, it challenged the geocentric model that placed Earth at the center of all motion. When Herschel discovered Uranus and its orbit did not quite match predictions, it led eventually to the discovery of Neptune through the subtle gravitational tugs on the outer planets. When galaxies were found to be rotating too fast to be held together by the visible matter alone, it pointed to the existence of dark matter, an invisible component that outweighs ordinary matter by a factor of 5. Each of these moments began with an anomaly, with measurements that did not quite fit, with a sense that something was missing or misunderstood. Not all anomalies lead to revolutions, but all revolutions begin with anomalies. What makes the 3.1/Atlas situation particularly compelling is that it is happening in real time, with modern instruments, in an era when we have unprecedented access to data and computational power. This is not a case of piecing together fragmentary historical observations or trying to extract signal from noisy data gathered with primitive equipment. We have exquisite measurements. We have multiple independent confirmations. We have sophisticated models and powerful computers to test hypotheses. And yet the puzzle remains. The object is there, visible in our telescopes, following a path we can predict, reflecting light we can measure, and it is telling us something that we are not yet equipped to fully understand. It is not that the data is ambiguous or uncertain. It is that the data is clear and contradictory, pointing simultaneously in incompatible directions. The object will continue its journey, indifferent to our confusion, following the laws of physics even if we do not yet fully understand how those laws apply to it. And we will continue to watch, to measure, to analyze, to debate, to search for the answer that makes sense of the data, because that is what science is. Not the possession of certainty, but the pursuit of understanding in the face of uncertainty. Not the comfort of having all the answers, but the willingness to sit with questions that resist resolution. Not the elimination of mystery, but the patient, methodical work of transforming mystery into knowledge, one observation at a time, one hypothesis at a time, one eliminated possibility at a time. And right now, with 3:1/Atlas, the uncertainty is profound, the mystery is deep, and the work continues.